All right, so hello everyone. This is week 5 of programming training, and this is probably gonna be also another shorter video because it's a lot more hands-on application. And in addition to week 4, both of these videos you guys should, or at least I recommend for you to not only follow along, but also to actually get a robot out and start trying and start programming it. And if you guys have any questions, feel free to contact us on our email. Obviously, we don't have that large of an audience, so we can probably help everyone out. So this week is week 5. We'll be going away from encoder or driving by time, looking more into encoders, and hopefully also introducing gyro and PID, but mostly encoders. And next week, hopefully, we can implement gyro with PID. Encoders, we don't really need that much PID. There is tuning for the PID, but it's mostly good enough. So here's a blurb on what we are as a team. And probably seen other videos, probably seen this slide many times now. So the training overview, probably seen this slide as well. Week 5 will be introducing encoders, PID, gyro. So week 4 recap, if we take a look at our push bot, we can see that we've created on Android Studio, we've created a version to not only move forward and turn, but also sidestep. Pretty nice methods are built on our push bot that we've written ourselves, and we're able to drive in a square. So 2 methods. But you might have noticed for turning that might have made it inaccurate with all these external conditions like the terrain you're on, battery voltage, your weight of your robot, all these different factors that can affect when you go by time, move by time, and we'll be talking about encoders. So even with the sidestep, we'll be moving. It's not as consistent as something can be achieved with encoders. So we'll go ahead and move on to actually not a lab time. We'll first be talking about our teleop and autonomous goals. So you might have seen this. Looking at autonomous, using encoders this week and understanding kind of motor counts of distance, and actually implementing it. Might require a bit of math, a bit of thinking, but not too much. And now talking on to encoders, gyro, and PID control. So encoders, they're devices on your motor to record the shaft's position or motion. And so this is something similar to kind of what we have, but basically the idea is you have your shaft, you have your encoder, you have some sensors that help with detecting basically how fast your motor is moving. And based off that, you can also get position, and from this, you'll be able to move more accurately. So the idea is when you move by time, you only move for 1-2 seconds, but how fast do you move? You have all these factors, the speed, your battery voltage, all weight, all these factors can affect how consistent your program is. And if you're moving long distances or even short distances, but you need to be very precise, you don't want to be having to deal with these inconsistencies. And so this is where encoders come in. This is where the idea of tracking the position of basically how many rotations the shaft has made, converting that to distance by using a bit of just math and a little bit of geometry, like circumference, that kind of thing. Seeing how many times your shaft has turned, which means how many times your wheel has turned, which means how much distance you've covered. And based off that, we can translate that over and see, okay, if we want to go from this target position to another target position, this is how much speed we have to put, and this is how fast we're going to go, and this is when we have to stop, this is when we have to start, and that kind of concept. And so for our motors that our team is using, we use the Yellow Jacket series from GoBuilda, and they give us pretty good documentation. And for your motors, you can probably search them up as well. But they give us our specs about our motor and our encoder. So here's the motor details, but encoder is I think encoders in FTC robotics is going to be relative and quadrature, and then the sensor type will be most likely magnetic, but this is mostly just conceptual stuff on how the motor encoder works. And if you're wondering how the motor encoder works, you can probably check out this link, which will be in the slides here, on how encoder works more in depth. And so possibly actually magnetic quadrature encoders. You can see how they talk about how you have 2 sensors, and you get this timing diagram, and based off this timing diagram, you're able to see which, not only how fast or how many turns your motor has made, how many ticks has been recorded, counts has been recorded, but also the direction based off the offset of these two sensors. But we'll probably not cover all this in depth. If you feel interested in wondering what it is, I'm not going to just like read it for you, but you can definitely click on this link and check it out yourself. And yeah, it's definitely recommendations. Pretty interesting to see how Encoder works, even if you're on the program performance. And so, let's continue on our documentation. So you can see this is really what we care about. Our encoder resolution is 537 pulses per revolution on the output shaft. And pulses per revolution, I'm pretty sure it's the same as counts per revolution. Actually, it might not be the same. But when we're programming our robot, that's going to be the number we're using, 537.7. Make sure I'm not lying to you guys. Yep. Okay. So 537.7. It might be different for some. Like I can imagine if you have like an Andy Mark, Never Rest 20. I remember these were really fast, but probably something similar. Encoder, 134.4. So you'll probably be using that number as well. But they give you there has to be some statistics here, right? There are some specs, but yeah, right here. And you probably just have to read through some of the documentation. So 134.4. And then yeah, it's also this information is interesting to look at for other stuff. Wow, like I never knew that my motor case temperature is 190 degrees, it'd fail. But yeah, let's go ahead. So you know that number, and that's gonna be a useful number for basically saying it's gonna this encoder when it reaches 537.7 pulses, should really be a whole number, but maybe it's like it's like 10 revolutions in each 5377. But so one full revolution of the motor, right? So when you can imagine, you see the shaft, and when the shaft turns one full revolution, the encoder will take 537.7 times. So when your shaft turns once, your wheel, based on your gear reduction, if your gear reduction is 1, so it's a 1-to-1 gear ratio. So you use your shaft and like you have your gear, another gear for your wheel. If your gear reduction is 1-to-1, or maybe your wheel is just attached straight onto the motor, then that means one full revolution of the wheel will be 537.7 encoder pulses per revolution for this motor. And so then, maybe your wheel diameter is 4 inches, and then you can do 4 pi. So in one revolution, you'll travel 4 pi inches, and you can do the math based off that to calculate, all right, if I wanted to move 5 inches, how far would it go? And First also has some sample code that we'll be using today that's particularly helpful for this. So that's encoders. We won't be covering Gyro and PID, but it's a pretty good idea, I think, to introduce it today. And so Gyro, the idea is your robot control hub or your phone itself, or I'm pretty sure even expansion hub, maybe. I'm not too sure about that. But the robot control hub for sure has an inbuilt internal measurement. Your phone does for sure too. But if you guys ever use like maybe an iPhone or Android phone with a compass, or those like calibration apps, if you've ever seen them, like if you turn, it can figure out like which direction you're turning and like the level. That's all based off an IMU. Also like planes, that kind of stuff. Anything that really needs to figure out angular position and velocity. So velocity basically in all 3 axes. So like the pitch, roll, or pitch. So pitch. By the way, if I'm always looking to parts, because I can't really car, but pitch and then roll and then yaw. That's kind of all part of the idea of getting that information from an IMU, from like a control. IMU stands for internal measurement unit, by the way. And so we really only care about the yaw. You can get all 3 axes, but hopefully your robot's not rolling or pitching. And so we only care about the yaw, and that will tell us where our robot is pointed. And so the idea is now you know where the robot is pointed, but if you want to move to its target set point, how do you do that? And that's kind of where PID control comes in. So PID control is a closed loop feedback system. If you don't know what that terminology, just don't worry about it. Basically, it just says if you have this certain error, we're going to try to take that error and correct it. And so we reach a certain set point. So let's say 24, you want to turn 90 degrees. Your error, it's 90 degrees. So then you use PID, and PID takes your present error and turns, okay, so you're 90 degrees off. So you got to go at this speed. Integral says basically look at your past error, and let's say maybe you've always been, maybe there's this force that is, maybe like there's a force that's pushing your robot. Maybe you're on a slant or something, and there's a force that's pushing your robot. The robot reaches the 90-degree turn, but then it drops off. 90-degree turn, it drops off. An integral will take your past error, that past error of dropping off all the time, and it will give it a little bit more oomph and push it across. Maybe it's the other way around. You're going 90 degrees, right? But you're going the other way around, and now when you're turning off the slant, and so you want to continue turning, but the integral takes that past error and kind of maybe even goes in the other direction to correct it. And then derivative is future error. So you can imagine if you're turning 90 degrees and you're going super fast, you might just overshoot, and derivative will take that overshoot, and instead of going and like kind of oscillating and trying to reach a point, it'll take that overshoot and correct for it and reduce the oscillation. And you'll see it probably more in application. We'll try building it next week. But yeah, so PID control is pretty useful for gyro. Encoders already have their own PID control. If you look at the documentation, I bet you can search up FTC, or I think GitHub and or FTC documentation. Oh, all right. And if you look at the DC motor X in the documentation, you can see they actually do have PIDF coefficients. So you can also tune the encoders itself. And there's also an encoder guide actually for tuning. So I think it's like a Google Doc. Google. Okay, maybe it's this. Yeah, so motor encoder guide. That's probably first, but this is also pretty useful for tuning your encoders when you're dealing with PID. Most of the time, you don't have to worry about it. It's already pretty well set up. And then, yeah, here's a motor PIDF tuning guide. I'll probably include these in the description as well for anyone who wants to check them out. Or actually, maybe I'll just include them in the slides. So I'll go ahead and put them, actually, I'll include them in the description for sure. But here is 2 guides in the speaker notes. And yeah, tuning guide, how PID works. It's pretty useful to learn. And you can also have tuning systems for your whole robot as well. And let's go ahead and keep on going. So that's, oh, we don't need these slides. Here's a cool diagram of PID. Actually, all these slides into one, but here's one on PID control and how it kind of works. So you take the error and proportional and referential, and you basically try to fix the error. Also, there's probably some, if you're interested in what, oh, look at that. Understanding PID control. This is also a pretty good playlist for understanding PID control if you're interested. So I'll go ahead and put that in as well. So here, from the description as well. Okay, let's keep it open. So great. But now on to the main part, and probably delete the slide. And onto the main part, let's actually set up encoders. And the plan today is to be able to set up a drive-in square method with encoders, not only using sidestep, but also turn. And it won't be hopefully too long. And next week, we'll be looking at gyro PID tuning. And so let's go ahead and switch on over to Android Studio. Here is Android Studio with the code from last week. And now let's go ahead and, so it's actually, we have to say goodbye to drive by time, but now we'll be moving on to drive by encoder. So we open up the samples over here. So Java or expressions bar, FTC robot controller samples. And we go to pushbot auto drive by encoder. And we can copy that and paste it inside our team code here, clicking on the folder and hit OK. And you want to make sure to open up the import again and get rid of the sample, delete that. And then we don't really need the documentation because it's kind of irrelevant, but we probably want to write a bit of our own later. So actually, we'll probably put it right here. So encoder based move in square. both turn and sidestep. So the idea is, well, one of the methods will be going forward and turning, but also turning. It's kind of tough with encoders because, you know, encoders are just, it's pretty good forward direction movement and left right movement, but when you're turning, that means you're rotating. You got some geometry, funky geometry you might have to work with, and so generally that's when we look at gyro. But we'll still create a turn one with encoder, just as part of the learning process. So let's go ahead and delete this really long branch that it's this external sample code hardware push button. So let's use our own that's in here. By the way, all this code is linked in other videos. So if you guys need any of the code that you don't have, maybe just starting off here, you can check out the previous videos for the most updated code. And this video will also have the finished code as well. So you can see how there's a bunch of red lines, and that's because the sample code had only left and right drive, but we're going to also include left front, left back, right front, right back. And so let's go ahead and, so this resets the encoder, which is pretty helpful at the start. So we're going to, instead of doing left drive, do left front, delete this line, and then we'll just create like 4 copies for each one. So front, left back, and right back. And then we have run using encoder, same idea. Delete one of them, change this to left front, and then copy, paste. And we'll change this to right front. And you can imagine if you probably do this live, you're gonna write a lot of programs. You'd probably write some hardware push bot method to just have one command that says, you know, set mode. And we can actually, let's do that actually. So we can create a method called, you can probably create it over here, public void set drivetrain mode. And then this would be DC motor. The type of the parameter passed in would be DC motor dot run mode. By the way, if you guys don't understand this, that's definitely okay. But if you want to try to understand it, then you would basically just check out you check out maybe like some Java New Boston tutorials. I probably have the link to the Java Crash Course to check that out. And the New Boston tutorial. Actually, I might not have it, but you can just search them up. The New Boston. I'll probably link it by the end of this video. So if it's not already linked. And so the New Boston is pretty good. It's beginner tutorials, help out with learning Java. So we want to set the DC to rotor.run mode. This is actually enough. Let's see. Why does this? I'm not exactly too sure why. Oh, DC motor.run mode. And then mode. And then we can go ahead and actually put this here, and then we can put this, we put the mode. For all 4 of them. And then we'll go ahead and replace whatever we had here with set drivetrain mode. And then we set all of them to DC. Using encoder now. So encoders. Actually, we'll put them as run without encoder, in our encoder-based program. So we'll change it up. And so we can go back in here and back to our encoder and get rid of all this. Simplify it to just robot.set drivetrain mode. DC motor dot run mode dot reset. So first stop and reset encoder, and then go ahead and set it to run with encoder. All right, there we go. And then we can probably just get rid of the telemetry here. You probably know, encoders all reset. That was the purpose of this, just to get the current position. But they're all going to be 0 because you just reset them and wait for start. And then you got this encoder drive, which will just basically wipe out. We're creating our own. So we have 4 motors, then the clause and the data. It's okay. So now we're going to be, here's our encoder drive method that they've created. And so this is where we basically just refactoring this to set up with 4 instead of 2 motors. So we have speed, but let's change our double left inches to left front, double right inches to double right front. And we're going to be taking, basically the method moves a certain amount of inches, but we're going to have to do that for all 4 motors. So double left back instead of 2. So, and then right back. And then the timeout is basically saying if you have spent 5 seconds on this task and you haven't gotten to your target position yet, just quit. But I think that's honestly not that good because for when you're first writing your program, you want to be able to have consistent results, and you don't want to be worrying about if a timeout has been hit or not. So we can just delete that. And so basically everything here, we're going to be changing it to adapt for 4. So we only have 2 targets right now, but we have to have 4 targets. So into the left front target. And actually, there's a neat thing called refactoring. So we can probably just refactor this so we have some kind of done. So it just changes every single thing that's this new left target to new left target. And then we can refactor RF target. And then we can just copy these and LB, RB, and then we'll go ahead and also, so now that we have the targets, ensure that it's still active. If it's still active, we set the position. So this new left target is equal to whatever the current position is, plus some conversion factor. So left inches, distance times counts per inch. And we'll be setting that up soon too. It's up there. It's the top of the file. So instead of left drive, we're going to do left front. And instead of right drive, we're going to do right front. Instead of this, we want to change that to Ella, or yeah, wait. Ella. Oh, no. You want to do whatever number of inches. So left front, well, left front as in left front inches. Then right inches is right. And then we're going to do the same for the other targets. And so this is going to be basically saying this integer is going to hold what tick position we want to get to. And so change this to LB, RB, and then change this to left, back, right, back. I'll change left front to left, back, and right front to right, back. And then set the target position. So add a space here. New left front, right front, or robot dot right front, sorry. And then we'll copy this over and then make this left back and right back. So now we'll be moving to the target position of whatever this new target position is. And then we'll go ahead and turn on run to position so that the motors will move and try to get to that position. So we're going to do left front, right front, and we'll try to start moving on, or have the motors be in the mode to start getting ready to, when we set this motor power down, we'll be setting the motor power and it'll be trying to run to the position. So basically turn the idea is you'll be turning the wheel to a certain position, but by turning the wheel a certain amount, you'll be actually moving the robot. It'll get to a certain position you're hoping it's going to be at. So left, back. And so now we're going to want all of them. So instead of 2 motors, we want 4 going to being, oh, let's use a handy dandy method instead. Robot dot set drivetrain mode, and then DC motor dot run mode dot run to position. There we go. Simplify that a bit. And so we'll reset, and then we'll set the powers. Instead of just 2, we'll set all 4 powers. And I think the neat thing about run to position is, even though you're going math.absolute speed, which doesn't make sense if you try and go backward, then why do math.abs? The run to position will move the motor in the correct direction. Back. and right back. And there we go. So while op mode, so this is, now we set the power, but now we gotta wait until basically when they reach a position, they'll stop being busy, so they won't be busy anymore. And so we'll not be trying to reach a position, so this will be false, and then this while loop will break. But the idea is the while loop will stay while the op mode is active, and well, we don't have a timeout anymore. So and all of them are busy. And so if you read in here, basically when any motor hits its target position, all the motors stop working. And so that's kind of a limitation. Maybe you want to get all of them moving, stop all of them, based off each target. But this generally works well enough, and the limitation is as long as you don't have too crazy motors, it should be okay. So for turning, sidestepping, all that kind of deal, it should be hopefully okay. So we can change this to left front is busy, so the robot left front, and the robot right front is busy. And then not only that, but we want to also include the robot.left back is busy and robot.right back is busy. Pretty long line, so enter. And then we don't have to display telemetry. We can just do this like while loop. So basically, it's just gonna be stuck in this while loop until either you stop the on mode, or one of them is or at least, or all of them are still moving. Once one of them turn into false, right? So once one of them are not busy, then the whole thing is just gonna stop. And then after they're not busy anymore, they don't need to run to position. We're just gonna set powers back to 0. Set powers 0. Use our handy dandy function, and then we're gonna turn off run to position. So we can do robot.set drivetrain mode DC motor dot run mode dot run routine instead of run to position. And then there's the optional pause, which is it's okay. You don't want to have random pauses. And that's about it. That's our method. Oh, looks like we are replacing it. So new LB target, new RB target. And then it looks about good. And then we'll go ahead and call that method now. So encoder drive, call it, and then let's have our speed be our drive speed. And then we're gonna go ahead, and this is gonna be, we can make a comment, drive in square with sidestep. So first we're gonna move forward, let's say 10 inches. So 10 inches, 10 inches, 10 inches, 10 inches. Not too much. And then we're gonna go ahead, so this is moving forward, and then let's copy paste it 4 times. And then we know that we're gonna have to sidestep. And so if we remember from the diagram, so have it, sidestep left, we're gonna have to move this one down. So left front down, right front up, left back up, right front down. So you gotta push the left sides in, right sides out. So left front, push it in, right front, out, left back, out, or actually, right, depends how you look at it, but you get the idea. So right back, so push left front's going in, left back's going in, and right front's going out, right back's going out. This image visualization, you can really think, oh, I'm making quite a bit of stuff, right? I'll just copy this image in. But go ahead and put it on. I'll just make a new slide. So if you guys want to use it as reference. You can also probably just Google it. And I'll go ahead inside. And so you get the idea. So then this is for sidestepping left, and then we're gonna move backwards, so all of them negative. And then for sidestepping right, we're just gonna go to the opposite of sidestepping left. And there we go. There's our sidestep method. You guys can feel free to test it out, try it out. And then debugging, if you guys have any questions, let us know. But it's probably gonna have to be processed to see where you might have gone wrong. But we'll also be attaching the code, so maybe you can do some comparing. And so that's sidestep. And then we can also try doing turning. Turning will definitely be a bit harder, but we'll have to do the same step, moving forward and turning left multiple times. So 4 times, and then idea is we'll have to encoder drive, we'll go forward, and then we're going to turn left. How do you turn left? Well, you have to make your left ones negative, and then your right ones forward. This -10 is probably not going to be the right amount of distance you want to turn. So we can do a change to actually. But I guess the neat thing about this is that eventually you might have a conversion factor if you do enough testing. But now compared to the previous method of time, this is at least a bit more accurate because you're actually measuring motor revolutions. And so eventually we'll be doing gyro. But this is definitely a great improvement, even if you're not doing gyro for just regular movement. So you have encoder drive, and then that's basically it. So you move forward, turn left, do that 4 times, and you'll hopefully turn in something of a square. But change 10 to actually move. And I think that's about it. That's encoder drive for you. So I'll upload all the links, and that's about it for today. Thank you guys for all coming and checking out the encoder drive, modifying hardware push bot a bit, modifying encoder a bit. I'll be uploading the files and uploading all those links that I was talking about, and hopefully you guys are able to learn something. So thank you for coming, and maybe see you next week.